Welcome back, everyone. In this lecture, we're going to cover the basic theory behind a recurrent neural network. As we previously discussed, we're going to be using recurrent neural networks on sequence data, which we've seen can be anything like time series data, like historical sales information. It can be sentences of words, even audio data, car trajectories, music, etc. Essentially, a sequence is just data that comes in a specific order, and the order is important to that information that's held within the data. So if you just kind of mixed around different words in a sentence, the order was actually important, because if you mixed around those words in a different order, the meaning will either be lost or just completely different. Same with time series data or audio data. So the order is also important here. So that's what makes it a sequence data set. So we can imagine something like a very simple sequence of 1, 2, 3, 4, 5, 6. And the question we're trying to answer is, would you be able to predict a similar sequence shifted one time step into the future? Now, if we're reading this as humans, it's probably easy to tell that the next number should be a 7, since it looks like the pattern is just add 1 as you go along. That may not be the correct pattern here, but it's a pretty reasonable pattern to assume here. So we would probably then predict that the next time sequence shifted just one time step into the future with the same number of elements would be 2, 3, 4, 5, 6, 7. So we want to say, are we going to be able to build a network that can learn from that history? So to do this properly, what we need to know is we need to somehow let the neuron understand and know about that previous history of outputs. It can't just know the 6 to produce the 7. It needs to understand that there was 1, 2, 3, 4, 5, 6. So how do we actually let it know about that history of its output? Well, one easy way to do this is to simply feed in its output back into itself as a new input along with the new input information. So let's take a look at just a normal neuron in a feed-forward network. In a normal neuron, we have inputs, so that will be a batch of features. So in our case, when we're dealing with sequence data, that would be something like some little batch of sequence in the sales data, or some little batch of sequence in an audio file. And so we have that input coming in, and often it's an aggregation of inputs, especially if this is some hidden layer or some hidden neuron. So we have an aggregation of inputs, and then we have an activation function, and then the output. That's how a normal neuron works. So how do we take advantage of being able to relay back history with a neuron? Well, we can use a recurrent neuron. And a recurrent neuron, the main difference here is not only does it send an output out to the next layer, it will take that output and feed it back into itself. So over time, we can unroll this. So let's go back one time step into the past at t minus 1. So we have some input coming in at t minus 1. So this can be a batch of sequence data. We would aggregate it, pass it through the activation function, and then we get the output of this recurrent neuron at t minus 1. Then, as time goes on, what we end up doing is for that next input batch of another sequence, so input at time t, then what we're going to do is not only do we feed in the input at time t, we also feed in that historical information of the output of the recurrent neuron at time t minus 1, which then gives us an output at time t, which then, as you can probably imagine by now, we go ahead and take that output at time t and feed it along with the input at time t plus 1. That way, we're retaining that historical information. And so this is the recurrent neuron essentially unrolled throughout time. Cells that are a function of inputs from previous time steps are also known as memory cells. And recurrent neural networks are also flexible in their inputs and outputs for both sequences and single vector values. So we can create entire layers of recurrent neurons. We already know what an artificial neural network looks like, and here we have just a normal RNN layer with 3 neurons. We're passing in some set of features X into these neurons, and then we get some output Y. So recurrent neurons, we just saw a single neuron, but keep in mind, we can apply the same principle to a recurrent neural network layer with 3 neurons, essentially taking that same output and passing it along as an input to each of these neurons. So then we can then unroll this layer in the same fashion. We pass in input at time t0, pass it into the layer, get the output at time t0, and then that output for that layer is then passed in to the layer at time t plus 1, t plus 2, and so on. Now, recurrent neural networks, as we mentioned, are very flexible in their inputs and outputs, and there's different types of architectures you can use here. Let's see a few examples. You can use a sequence-to-sequence model. So this is also known as many-to-many. Essentially, you pass in a sequence and you expect a sequence out. So for example, given 5 previous words, go ahead and predict the sequence of the next 5 words. And you can use this for something like, if you get a question of 5 words, go ahead and predict the answer of 5 words. Keep in mind that your data would have to reflect this. Your data would have to be matching sets of sequences of something like a question to an answer. And theoretically, we could train a chatbot if we had a data set large enough for this sort of thing. Then there's also a sequence to vector. This is known as many to one, where we're essentially just passing a sequence and then predicting a single value. So for example, given 5 previous words, go ahead and predict the next word. So we can use this to generate text. Given 5 historical words, what's the most likely next word after this? Then there's also vector to sequence, one to many. So maybe given 1 word, go ahead and predict a sequence of the next 5 words. A basic recurrent neural network also has a major disadvantage though. We only really remember the previous output. If we think back to that unrolled diagram, we were only feeding in the output of 1 time step into the past. And what happens is, if we have really long histories, we begin to start to forget the older historical samples, since we're only really looking at the output of the last previous t-1. And it would be really great if we could keep track of longer history, not just that short-term memory. Another issue that arises during training of a basic recurrent neural network is known as the vanishing gradient. So what we're going to do is we're going to explore this idea of vanishing gradients in more detail before moving on to discussing essentially an expanded idea of the recurrent neuron called a long short-term memory unit. And the long short-term memory unit solves this problem of only dealing with short-term memory of the previous historical output at t-1. We're going to be able to have a long-term memory and a short-term memory. So before we do that, I want to talk about vanishing gradients, and then we'll move on to discussing LSTM units. And after that, we'll have all the theory we need in order to begin programming this with Python. I'll see you at the next lecture.